didn't die until 1912, and so we have an actual photograph of this guy. And he was the first person that discovered the theory of chaos. And he did that by, well, there was a contest, I think in 1889. It was for the king of Sweden and Norway, so he was king of both of those places. It was his birthday, his 60th birthday, and they decided to have a contest. And it's not like modern contests where you enter online to win an iPod. The contest was to write a 200-page paper about some unsolved problem in mathematics. And Poincare decided to write about the stability of the three-body problem. So the three-body problem is a system with three orbiting bodies. So that would be like the sun, the earth, and the moon. And he wrote this 200-page paper about it. And he found that, and he did win the contest after a while. After some controversy, I guess there was controversy in those days about mathematics and that. And in his paper, he discovered that for certain orbital, or for certain parameters, so for certain masses of the three bodies and at certain distances, that the motion became irregular, or what he called chaotic. And so what are some of the symptoms of chaos? If you had chaos, let's see if this will work. What would some of the symptoms be? Okay, so this is a little applet showing a double pendulum. And a double pendulum is a chaotic system, but for certain displacements. So here it's oscillating back and forth with a very small displacement, and you can see the motion is nice and regular. It traces out these things that look like lists of juice figures. But if I take this pendulum and displace it to a large angle and let the system go, so the graph will zoom back in. The graph is plotting the two angles that each of those pendulum arms make with respect to the vertical. You'll see that the motion becomes erratic. Sometimes the pendulum behaves as one pendulum, sometimes the bottom one spins around, sometimes it flips all the way over, like that. Perfect. And eventually, if we wait long enough, this pendulum will visit all the places in that phase space. And that's one of the symptoms of chaos, that it's unpredictable. Well, it's unpredictable, but it also visits every single place in phase space. So I'm going to let it run for a while. Maybe we'll visit it later and see how it's doing. Okay, so it's apparent random motion for certain parameters. Also, two neighboring positions quickly diverge. So this is another symptom of chaos. So if you think about the game Plinko. So here's a demonstration that shows something like the Plinko game, where you have, here has three balls. So here they are, and they all enter the Plinko board at almost exactly the same spot. And even though they enter at almost exactly the same spot, so the separation between them is very, very small, the path they take eventually diverges, and you can't predict, even though you know the starting position to some very small accuracy, what's going to happen when, or where the ball is going to land. And this makes the motion highly unpredictable. And let's see if we can hear my example here. So this is Jennifer, and she wins. Okay, so did you hear Bob Barker? He said if you put it exactly in the same place and release it, you'll win the $5,000 again, because now you know where the track is, you know where to place it. So what do you think? Do you think she's going to win the $5,000 again? No. So she's going to do it again. Let's see what happens. One more. Oh. The Plinko chip does. The Plinko chip is hung up. Now this doesn't. So, okay, so we're filling in some more of our pendulum here. Okay, so the motion is unpredictable in that sense, that even if you know two starting positions and they're really, really close together, that doesn't mean that what you see in the end is going to be exactly the same. So that's another condition or symptom of chaos. And furthermore, it can be a small part of an otherwise stable solution. So like we see with the double pendulum, that for small angle displacements, the motion is regular. There's nothing, not that it isn't interesting, but there's no chaos involved. But if I displace that pendulum to a large angle, then I get the chaotic motion. Okay. So, where do we see chaos in the solar system? Well, the answer is in a number of places. One of the most significant ones, though, is in the asteroid belt. So the asteroid belt is a whole bunch of asteroids that occupy the orbits in space between Mars and Jupiter. There are a whole bunch of them, and they give certain ones different names. If they're Earth crossing, they call them Apollos. If they're near in Jupiter's orbit, they're called Trojans or Greeks. And if you start counting up asteroids, and you count them up based on what their orbital period is. So if I start counting and I determine that this particular orbital period, there are more and more asteroids, I'm going to give it a large line here. Whereas if there aren't any asteroids, you'll see a gap. And you get a very interesting diagram. This was first done by Kirkwood. And you can see that there are gaps that occur, and they occur at certain orbital resonances with respect to Jupiter. So for example, this gap here, it says 1 to 3. So that means that asteroids that would be found in that gap go around 3 times for every 1 time that Jupiter goes around. Let's see what else we have here. This is the 2/5 gap, so that means that for every 2 times Jupiter goes around, those asteroids would go around 5 times. And we don't see those asteroids. And the question is, well, why not? And so here's a little animation. This actually shows the moons of Jupiter as they go around. And the moons of Jupiter are in orbital resonance. But you can see what happens, that if they're in a certain orbital resonance, they meet at the same place over and over and over again. And when they're a little bit closer like that, Jupiter can tug on those asteroids a little bit harder, because remember, the universal law of gravitation tells us that if the closer the 2 objects are, the larger the force between them. And so as they meet again and again at the same position, Jupiter can tug on them and knock them out of that orbit. But is that the whole story? Well, of course, the answer is no, it's not. So, for example, there are places in these orbital resonances, such as the 2 to 3 resonance here, where we see an overabundance of asteroids. And so if that was the whole story, that it's only the case because those 2 to 3 resonant asteroids should experience the same regular poles that say the 1 to 3 asteroids were experiencing. And so why is there an overabundance of asteroids there and an underabundance in other positions? And the answer is, well, it seems like there's chaotic behavior in the asteroid belt. This figure is taken from Jack Wisdom, who's big in orbital mechanics. His thesis, I think around the year 1980 is when he did this work. And what he did is he populated a model solar system with a whole bunch of asteroids near the 3 to 1 orbital resonance, and let the simulation go to see what would happen. And it turns out that those asteroids are stable for millions of years. So this is a plot of eccentricity versus time, so how elliptical their orbits are. And then all of a sudden, for seemingly no reason, the eccentricity will experience these huge jumps. Alright, so if I have an orbit or an asteroid and it's orbiting and suddenly its eccentricity changes by that large amount, so up to a little bit over 0.3, suddenly it's going to be cast out in a very elliptical orbit, and it might come into the inner solar system further than it normally would. And if that happens, it's going to cross the path of Earth or Mars or Venus and either collide with that planet, or maybe it'll experience a gravitational flyby and be ejected. And so that can explain the reason why those gaps occur, and maybe not so much the other explanation.